And my name is Siegfried, and today I will talk about the dark and hidden sectors, and I will also cover something called the Higgs portal. So let's begin. I will start with this quote from Steven Weinberg, who said that we all agree that there has to be something beyond the standard model, but we don't know what that something is. So Steven Weinberg, of course, he was one of the people who worked a lot on the standard model, on electroweak, and he actually also did a lot of work on dark and hidden sectors. He unfortunately passed away last year, but he has been a big figure in this field. So let me just briefly go over the table of contents of this talk. So I will go first over the background of hidden sectors, and then I will show some hidden portal models, and in the end I will also show a dark matter example. So, as for the background, when we talk about hidden and dark sectors, it's always beyond the standard model. This is not something that is covered by the standard model. So what we do with hidden and dark sectors is that we introduce a collection of quantum fields, and then, of course, these quantum fields get their associated particles as well. And this is what we introduce with these hidden and dark sectors. These sectors also have to interact in a weak way with the standard model, and by weak I don't mean like the electroweak interaction, but I mean like as in the sense that it's not strongly interacting. Otherwise we would have seen them experimentally. The interactions also must be indirect, and they must be either like mediated by gravity or some sort of other new force mediator that we don't have in the standard model. And hidden and dark sectors are usually associated with dark matter. That's very common. So, as for some examples of hidden and dark sectors, we have the Higgs portal, which is a scalar boson, so spin 0. We have sterile neutrinos, which is spin 1/2. This is fermionic sectors. We also have dark photons, which is a vector boson, spin 1. And these three examples at the top are the main examples which I will be covering today. But there are also a lot of other examples. So we have axions, for example. These are spin 0, so they are scalar bosons. And these aim to solve the CP problem of the strong interaction. And this leads to something called the PQ symmetry. And in this field, the axions, it was actually here where Steven Weinberg did some nice contributions, actually. And there are also this, for example, this X17 particle and field, which is kind of controversial because some years ago there were some indications of that some people had seen them in experiments, but later on people haven't been able to reproduce it. But it's used to explain the anomalies in, I think it's beryllium 8 decay or something. There is some sort of decay where this particle is used. But it's kind of controversial, so I won't be talking about it today. And all of these, of course, are used to explain anomalies in experimental results or like theoretical shortcomings. So this is why you introduce these sectors. So often when you want to do these hidden and dark sectors, you introduce a new gauge group. And this gauge group is often independent of the standard model gauge group. So we have the normal standard model gauge group, and then we have the dark and hidden gauge group. So this new gauge group, it can kinematically mix with the standard model group, and this then allows for interactions between the standard model and dark matter particles. I will explain this kinematically mixing later on. And we have some string theory predictions that these hidden and dark sectors exist. So if we can find these sectors, we can basically, that's one way to show that string theory might be a viable option. And these hidden and dark sectors are, of course, sources of dark matter, which I will be covering, and also these sectors can contribute to the breaking of supersymmetry if it exists, because we haven't seen any supersymmetric particles with the same mass as the standard model particles, so the supersymmetry must be broken, and this is one way to explain supersymmetry breaking. Right, so let me go over some hidden portal models of the dark and hidden sectors. So the premise is that we have no signs of new physics at the LHC in the form of an energy resonance. Like in the way that the Higgs model was found, we found this energy resonance at 120 something GeV. But we see no other kind of resonance that looks like this for new particles. So there are two options that this might be hinting at. Either the new particles have a lot higher masses than what is reachable at the LHC, or the production rates are too low, such that it blends into the background of the LHC, so that the bump is not statistically significant. But this also hints at some other properties of these hidden or portal models or dark matter models. And it's that the LHC triggers don't respond to these final states. That's one possibility. Then we wouldn't see them in the LHC. The new particles may only decay hadronically, for example, which would be bad, because then these decays would be buried in the QCD background, which is very difficult to see because there's a lot of QCD background. We discussed this during the experimental lectures, that the LHC is not like a precision machine, it's more like a discovery machine, and it's you get a lot of background from it's very dirty signal, so to say, because you have a lot of gluons and quarks inside the protons. Otherwise, we could also have that the new particle is produced in association with other particles, maybe other dark matter particles or standard model particles, which could mean that it's also difficult to detect. And this dark matter particle or hidden portal particles could be very, very close in mass to other standard model particles, which would mean that maybe they are inside the same decay width, and you can't differentiate between one particle or the standard model particle because they are very similar in mass, because mass is what we often use to differentiate different particles. So these are all different properties that the hidden signatures could have, which would also make it such that we don't see them in the LHC. So I will be covering these three hidden portal models. So the first one, the Higgs portal, which is again the spin zero, the scalar boson model. I will be covering the neutrino portal, which is often called sterile neutrinos, which is the fermionic spin 1/2 portal. We have the vector portal, which is the dark photons. So this is a spin 1. One of the examples is the dark photons. So this is spin 1 vector boson again. So starting off with the Higgs portal, this is just one example that one can do. You can, almost like Magnus just a few minutes ago talked about, you can introduce a Higgs portal model with an additional real singlet. So in this case it's a singlet, not a doublet, but it's a real singlet scalar field, X, which means that we also impose that it mixes with the standard model Higgs doublet in the presence of this new Z2 symmetry, which we have seen in the assignments and plenty of presentations before this. We also have that X is odd under this Z2 symmetry, which would mean that we have no X or X3 terms in the Lagrangian, because the standard model fields are even under Z2, which would mean that any Lagrangian terms with just X or X cubed would be not invariant under Z2. Okay, so the Lagrangian for this formulation, this model would have the kinetic term of this new X particle. We would have a similar potential as for the Higgs particle, the Higgs field here, and then we would also have the interaction term between this new X particle and the Higgs boson, the Higgs field in the standard model. And then we also add, of course, this standard model Lagrangian. So these two new fields, the old field phi, which is the Higgs field, and this new X field, they are expanded around their vacuum expectation values. Of course, we have seen this just a few minutes ago with this phi and chi, and then we rotate these fields into the mass eigenstates, so we get the Higgs and the new scalar bosons of the models are this H and HS. That's like the new particles that. So the H is still the old Higgs boson, the HS is the new scalar boson that we introduced in this Higgs portal. And this HS can then decay into standard model particles because we have this mixing. So the mass eigenstate is not purely the interaction eigenstate, but it's mixed with the Higgs boson. And the Higgs boson, of course, can decay into standard model particles, so we can have that HS can decay into standard model particles. But it's very suppressed for small theta, as you can see in this matrix, because it mixes with the sign of theta, and if you have small theta, then the sign is very small. Okay, so how could you see this experimentally? Well, detecting a new scalar is very difficult because it has mostly hadronic final states, and this means a lot of background. But there is this 4-lepton final state, which is called the golden channel, because it has like a small and very controllable background. So this is actually what Atlas and CMS is using to search for these Higgs portal models. Right. So for the neutrino portal, the fermionic spin 1/2, we know that we have neutrino oscillations, and this means that neutrinos must have non-vanishing mass. And this means that new physics is required because the standard model doesn't grant neutrinos any mass at all. And we see in the lectures that there are different ways to grant the neutrino mass, and these models are often called sterile neutrinos or neutrino portal models or heavy neutral leptons. There are different ways and different models. And one example is the type 1 seesaw mechanism, which we also seen in class. So it's one theory for giving mass to the neutrinos. So we introduce a right-handed neutrino, which couples to the active neutrinos and also the Higgs field through Dirac mass terms and Majorana mass terms. And these neutrino rights, they can mix with active neutrinos, and this leaves then a light and a heavy mass eigenstates. The light mass eigenstates are the active neutrinos that we see, the electron neutrino, mu neutrino, everything, and then we also have these heavy eigenstates. So this is like the neutrino portal that could also explain new physics. And experimentally, how we would see them? Well, you could use lepton number violation when looking for heavy neutrino signatures. And the great thing about lepton number violation, as we've seen in class, is that the standard model predicts no such lepton number violations, so we have no background in the standard model, which if you also done the assignments, you can see that if you have no background, and it's very much easier to get some sort of exclusion potential when you want to do experimental observations. For the vector portal, it is very often for beyond the standard model theories to introduce like new gauge symmetries, of course, and U1 prime is very common. It's used a normal U1, but we assign it with a prime to differentiate it with the normal U1. So this U1 prime, for example, if we introduce it, it can mix with the standard model U1. So we get this mixing of the two gauge symmetries. One example of this is that we get a dark photon which can arise from this U1 prime. One thing to note is that if we break this U1 prime symmetry, the dark photon will not be massless. So this is not like a photon in the sense that it's massless, but it's called a dark photon because it's a spin 1 particle. But it's not massless. And this dark photon can interact with electrically charged standard model particles due to this mixing between the standard model photon and this photon. This means that it can be detected. But this mixing is very, very small, or it's constrained to be very small, so it's very, very hard to detect. And some theories actually do not break this U1 prime symmetry, and this then leads to a massless dark photon. And this could be very nice. Okay, you have a massless dark photon, which would mean that you could potentially have long-range interactions as compared to like the W boson. It has a lot of mass, so it has very short-range interactions. Of course, there are other massless particles such as the gluons, which only have short-range interactions, even though they are massless. But potentially we could have long-range interactions if the dark photon was massless. But the thing is that if you have a massless dark photon, it's very, very difficult to discern it from the standard model photon because they basically would have almost the same properties. If there's no mass, they both have spin 1. Yeah, as you can imagine, it's very difficult to test it experimentally. And of course, with these vector potentials and other models, you can also add new Dirac fermions if you want. It's possible, and people have done it previously. Right, so quickly the last example, I will give a dark matter example, which comes from these hidden portal models and dark and hidden sectors. So, if you have a model which you introduce, the model at hand will decide the dark quantum number. So, for example, the dark quark flavors is decided by the model. You get dark charge assignments from the model, and you can use these dark quantum numbers to then decide if you have stable or decaying hadrons, for example, because they must satisfy some conservation laws. For example, if you assume these conservation laws exist in your model. And this, then if you find these stable or decaying hadrons, you can use this to find which processes contribute to the freeze out of the dark sector during the expansion of the universe. So we talked a bit about this, but the freeze out is basically that you have some sort of, in the beginning of the universe, you have this thermal equilibrium between, let's say, then standard model particles and dark matter particles. And you get an inflation, you get an expansion of the space, you get lower temperature, and at lower temperatures the dark matter particles cannot be produced because this thermal equilibrium is then cut off. But so you only get annihilation of dark matter particles, but then basically the expansion of the universe makes it such that these dark matter particles are too far and few between, so they cannot annihilate with each other. So you're left with this like dark matter relic density. So you get dark matter, which we now observe today, which comes from this thermal equilibrium. So then we can know which particles, for example, in our model can contribute to this. So in order to fit like cosmological observations, you get very, very tight constraints on the dark sector. So basically, for example, the charge of these dark matter particles must be very constrained. They must be neutral. That's a very tight constraint. The relativity of these particles is very constrained as well. I believe that we previously did a lot more hot dark matter, so relativistic dark matter. But then I think we concluded that these dark matter candidates would be not reminiscent of what the structures we see in the universe today. So that's why we have WIMPs and SIMPs, for example. They must be massive such that they are not relativistic. So now we look at more cold dark matter candidates. So that's you have a lot of more cosmological observations that put constraints on what the dark matter must be. So one example is from Banritter and others. They introduce like a dark pion and then this dark rho meson, where the dark pion is stable. And you would have this thermal equilibrium between these two dark particles, where they just become each other and annihilate and become each other all the time. But then you get this inflation and in the beginning of the universe, and this then creates the relic density of these pions, because they are stable particles, and these rho mesons, they annihilate to the standard model. So the rho mesons would be gone, so you couldn't create any more pions, and basically you would be left with a relic density. So this is a good example of dark matter. As for the sources I used in this presentation, you can see that they are very, very new. Most of them are published 2021. This one is published 2019. So this is very ongoing research that people are doing right now, and doing tests at LHC, of course, but also predicting what things might be out there. And hopefully one day we will see some results from these theoretical predictions. Thank you for listening.